it's your boy. Oh, we got the background. Not right now. Well, it's your boy JOSHABRAHAM. We're back. We're back. We're back with the studies. Because we gotta pass some exams. Because we gotta do some So I was confused on the metal band, the valence band, kind of valence band. What were the two bands? Conduction band, right? Uh, Conduction band, yeah, valence and conduction band. Exactly, you're on the right track. Just a few clarifications to make. Valence band form from molecular orbitals that arise when valence orbitals of all metal atoms combine, mostly filled with electrons. Electrons here are bound more tightly, still delocalized across the lattice. Conduction band formed from higher energy molecular orbitals in the lattice can be partially filled or overlaps with valence electrons. Electrons in the conduction band are free to move, which gives metals their electrical conductivity. What? Why conduction band exists? Slash fills up. Depends on the number of valence electrons per atom and how many orbitals are available on the band. If the valence band is completely full, electrons cannot move. The material behaves like an insulator. Oh, if you think about it, if electrons pair up with positive negative, they kind of cancel. Hmm. Kind of makes sense. Kind of makes sense. Kind of makes some sense. To the wall, standing on. What the fuck? Q? What the fuck is a Q? What's that a Q? Come take my hand, let's stick together to the wall. Whatever with the to the wall. Eminem, bro. Eminem sometimes just fucking does it. Dude, my watch is charging. Where's my phone? Ow, 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 ow. Each metal atom contributes its valence electrons to a giant sea of electron and sea energy levels. Okay, so now could you give me examples on metals that fills in the valence band and conduction band, so Does all the metals fill in the valence? Also, I just noticed that if the conduction band is full, it'll act like an insulator. Then the valence band that's filled is already acting like an insulator, or is it just for the conduction band? Now, let's take sodium. Sodium is a sample 3s1 filled from lower orbitals, partially filled 3s band, metallic conductor. Aluminium. Aluminum. Aluminium. Aluminium. That's good. 3s2, 3p1 form valence band, 3p partially filled conduction band. Okay, so from the looks of it, s orbital is primarily valence band. Uh-huh. Oh, I hate fucking black and yellow. Black and yellow, black and yellow. Who the fuck wrote that song, bro? All metals have lower energy bands filled. Are they much faster term compared to the band face conduction band? That's by metals conduct. They have partially filled conduction bands or valence slash conduction band overlap. Now we're getting more and more weird. Okay, so from what I have seen, the s orbital is the valence band, and the p orbital kinda acts like the conduction band. Conduction band. Conduction band. So how is how is d or f orbital gonna look like here? Also, when you said valence bond, valence slash conduction band overlap, how are the orb looking like? Is it the sp3 etc, or it's just exactly the same size of the outer, no height? Most incredible. I'm still here. Come on, figure it out, figure it out. SPDF orbitals in the metals and their bands. S orbital, usually the outermost electrons in alkali and alkaline earth metals. The s orbitals form the valence band, and the partially filled s band is also conduction band in some simple metals. Oh shit. Blood? They also form the conduction band. D orbitals in transition metals. The d orbitals are more localized than outer s orbitals. Filled d orbitals form low energy valence bands. Partially filled orbitals can contribute to the conduction, giving metallic properties. Key point: the band is not sp3 hybridized orbital. They are delocalized molecular orbitals extended across the entire lattice, so spread out. When we say valence and conduction band overlap, each atom brings its outermost orbital. When atoms are packed into lattice, these orbitals combine into molecular orbitals, forming a very dense set of energy levels. Because there are so many atoms, these levels are so close in energy that they form a continuous band. If the top of the valence band electrons with the valence band overlaps with the bottom of the conduction band, electrons can move freely. metallic conductivity. So no hybridization like sp2 is involved. Its orbital shapes in the lattice do not change like a covalent molecule. They just spread out and overlap across all atoms. Mm-hmm. Because there are so many atoms, these levels are so close. So no hybridization like sp2 is involved. Mm-hmm. Also, they use also the sentence of saying that if the conduction band is filled in, then it acts like an insulator. Could you explain on that? My eyes, bro. Yes, this is a crucial concept from band theory. Let's break it down carefully. Bands in solids and metals are solid. The atomic orbitals combine to form bands. Valence band, the highest energy band that is fully occupied with electrons. Conduction band, the next higher energy band, which is empty or partially filled, allowing electrons to move under an electric field. Electron flow conductivity. Electrons may be able to move into unoccupied states. What? Atomic orbitals combine to form bands. The highest energy band that is fully occupied with electrons. The next higher energy band which is filled, allowing electrons to move under an electric field. Electron flow equals conductivity. Why filled conduction band behaves like an insulator? If the conduction band is completely full, all possible energy states in that band are occupied. Electrons cannot move to a higher energy state within that band. Pauli's exclusion principle. Even if you apply a voltage, electrons cannot accelerate because there's no available state to move into. Hell no. This material behaves as an insulator. Metal, partially filled, good conductor. Insulator, full conduction band. Large gap to next empty band. Semiconductor, small gap. CB empty at 0 Kelvin can be excited. Conductivity depends on temperature slash light. Think! Why? I don't want to touch my screen. It's a lot of women. These kind of musics are so bad. Oh no. Ba, ba. All the way up. I say all the way up. Okay. Could you again explain the part of electrons where if their orbital is filled, it cannot move freely as compared to a partially filled orbital based on the wave nature of electrons. Like why is the electron not conductive on a filled orbital? Mm-hmm. YMC. Let's go deep into the wave nature of electrons and why field band cannot conduct. Electrons has wave in a lattice. In a solid, electrons are not just particles localized to atoms. They behave as waves that extend over the whole lattice. These waves form allowed energy states and bands. Each allowed state corresponds to wave function with a certain momentum. Each allowed state corresponds to wave function with a certain momentum. Each allowed state corresponds to a wave function with a certain momentum. Each allowed state corresponds to a wave function with a certain momentum. Pauli's exclusion principle plus wave nature. Each wave function slash state can hold two electrons with opposite spin. If a band is completely filled, all the possible wave function for the band is occupied. Electron as a wave needs an empty state to change its momentum. Electron as a wave needs empty state to change its momentum. If a band is completely filled, all the possible wave functions for that band are occupied. All the possible wave function for that band is occupied. Electron as a wave needs empty state to change its momentum. When voltage is applied. So, wait. So when you apply voltage, the wave nature of electrons excite. So why field bands cannot conduct? Applying an electric field tries to shift electrons to nearby higher energy states. Applying electric field tries to shift electrons to nearby higher energy state within the same band. If the band is filled, it cannot, the electron cannot change its wave vector. It cannot gain net momentum. No current flows. Okay. Why field bands cannot conduct? Applying an electric field tries to shift electrons to nearby higher energy states. Okay, I understood that if there's free space, voltage can help the electrons to increase wave momentum, and if there is space inside the orbital, the electron can jump to higher momentum. But how is the same orbital higher? Like, if there's free space in the same orbital, when voltage is applied, how does the higher momentum results in the same orbital? Like, it should jump. It should not just I'm kind of confused on that part. Partially empty seats, people can move, net flow, conductivity. Okay. Okay, so I need more explanation on this. Also, another question I have is how is the voltage, external voltage that results in higher wave moment for the electron is only possible if there's free space on the orbital. Then I thought having higher energy is about jumping to higher orbitals. Okay, I guess it's like, yeah, if you... Okay, now that I think about it... What the fuck did I write here? Get it. Think about it. If we apply enough voltage, the electrons gain enough momentum to jump to higher orbital, thus conducting electricity. So if the applied voltage is low, then partially filled orbital gains that energy and move conducting how it, I'm still a bit confused on how the freeness inside the orbital results in conductivity. Ba, 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 ba. 30 minutes? Go, damn. Go, damn. Devoto did. Hi, Josh. Hey, yo, what's up? Appreciate Devoto did for checking out the stream. Let's break this carefully and connect it to wave nature of electrons, bands, and applied voltage. Electrons in a crystal as waves. In metals or solid, electrons don't sit in isolated orbitals, they exist as a wave function extended over the lattice. Hmm. Okay, so if it's a whole lattice, then fully filled valence. uh, Then fully filled valence orbitals should conduct electricity. The fuck you yapping, brother? In the metal or solid, electrons don't say okay. The wave function corresponds to a state with a certain energy. The states in the solids form bands because many atomic orbitals combine, like molecular orbital theory, but for lattice. Oh, bro, that's a weird sneeze, not sneeze. Kinda, kinda, kinda. Motion requires available states. An electron in the wave function cannot simply increase its momentum arbitrary, arbitrarily, arbitrarily, arbitrarily. Oh, I hate the words. To accelerate, the electron must shift to a nearby wave function with slightly higher energy and slightly different momentum. If all the states are filled, there's nowhere for it to go. How? Uh, this is why completely filled bands is not conductive. Motion requires available states. An electron wave function cannot simply increase its momentum arbitrarily. Arbitrarily. I'm actually. It's arbitrarily. 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 Arbitrar. Arbitrarily. Arbitrarily. Dude, I'm wasting time. Focus, focus. Motion requires available state. An electron in the wave function cannot simply increase its applied voltage and partial filling. And a small applied voltage provides a tiny energy difference across a solid. Partially filled bands have empty states very close in energy. Electrons can shift into these nearby states. If the voltage is, you're correct, if the voltage is very high, electrons can jump from a filled valence band to a higher conduction band. That is what happens in insulators or semiconductors. Metals already have partially filled bands, even a small voltage enough to move. Okay, good conductivity, free to move inside a band. Conductivity. So so no, it's half. Come on. Next 30 minutes timer. Mm-hmm. It's not looking good. Dude, I'm tired with this fucking. Can you just not be stupid? Can you just work? Devoto did. I'm not. I'm guessing you're not on the stream right now. I'm gonna refresh the chat. Okay. Okay. So my another doubt. Uh, if let's consider fully filled valence orbital and no conductance orbital. So I'm guessing it's a lattice. then how or where is that given voltage is going? Like, does the wave nature just consume it? Imagine a lattice of atoms, all the electrons in the pair. This means no empty state. External voltage tries to push electrons, giving them tiny energy difference. The electrons can only accelerate if there's available nearby states. The electric field from the voltage still exists across the material. The energy does not disappear, but the electrons cannot absorb it in the form of motion. For a perfectly rigid, fully filled band, the energy is effectively stored in the electric field across the material. Electric field. Mm-hmm. Not gonna lie, my stupid brain is not figuring out electric field, what electric field is, or how electric field is made. But okay, that's a good electric field. Uh-huh. So given voltage is converted to electric field if there's no space for okay. Wave electrons as wave have quantized momentum in the lattice. The small voltage shift fill band okay states Pauli's exclusion principle. The electron waves cannot change. Energy is blocked from producing motion. How conductance can occur anyway. If the voltage is high enough, okay. Key analogy. Think of the electrons as water in completely filled pipe. There is no empty space-time stream. Okay, I'm really interested in the electric field. Okay. Okay, this looks really interesting. Could you explain what was electric field? Because right now my brain is not coming with the correct explanation on how electric field is made. So could you explain how the voltage is converted to electric field then due to the band? You live like this. What is an electric field? An electric field is the region in space where charge experiences a force. It is created by difference in electric potential. Met difference in electric potential, so one side gets a voltage, the other side does not have it. Electric potential difference. When you connect a battery or a power supply to a material, the positive terminal attracts electron and negative terminal. This separation creates a potential difference across the material. The electrons in the material feel a force proportional to the electric field. Electrons cannot accelerate because there's no. The electric field exists, but electrons cannot gain momentum. Think of it like water in a complete. Okay, where does the energy go? How does conductivity happen eventually? Okay, so electric field forms when there is a polarity inside the lattice. And how does the voltage results in that polarity that results in electric. How does the voltage result in the polarity that results in a, like if the electrons cannot move in a fully filled orbital, how do they rearrange to form the positive and negative terminals for the electric field? Yes, that's an excellent and subtle question. Stop glazing, brother. Or stop glazing, GPT. I am that intelligent. Voltage and polarity. Voltage is literally a difference in electric potential between 2 points. When you connect a material to the battery, battery's positive terminal attracts electrons towards it. Battery's negative terminal pushes the electron away. Battery's positive terminal attracts the electrons. Even if electrons cannot flow freely in a fully filled valence band, electron cloud can slightly shift within each atom or across the lattice. This shift is tiny. Electrons cannot move to a new state, but they slightly distort their position. This distortion creates a tiny separation of charge, which effectively a polarization of the lattice. Okay. So there is still a sort of. But on what basis do they move? Because. Mm-hmm. So, uh-huh. Hmm. Dude, these songs are amazing. No, door. This tiny displacement of electrons. Okay. Mm. Dude, my hands are cold. Let me just heat it up. Okay, you know what? If I go deeper, I'm gonna waste a lot of time. Ah, I hate it. Uh, Conductor partially filled or overlapping orbitals not relevant. High electron move electric high electrons move freely. Insulators fully filled. Empty large band gap very low. Electrons cannot jump to conduction band easily. Semiconductor fully filled. Empty small band gap moderate. Electrons can jump to given energy. Ah. Conductivity depends on how easily the electron. Metals, no band gap. Semiconductors, small band gap. What decides the band gap? Doping. Doping intentionally adding impurity atoms to a semiconductor to increase conductivity. Semiconductors have small band gaps, but pure ones are not very conductive at room temperature. The main types N type add atoms with more valence electron than the host. Okay. Example phosphorus in silicon. Silicon doped with phosphorus. Extra electrons goes into conduction band easily. Charge carriers electron negative. P type add silicon doped with aluminum. Add atoms with fewer valence electron that host. Creates holes in the valence band. Electrons from neighboring atoms can move in to fill in. Charge carriers electrons negative. Charge carriers holes positive. Undoped pure semiconductors. Only thermal excitation can move electrons to conduction band. Doped, what is worse is undoped. Undoped semiconductors, limited conductivity, only a few electrons thermally excited. Doped semiconductors, much higher conductivity. Electrons or holes dominate depending on type. Quick summary. Conductor, electron already free, high conductivity. Insulator, electron stuck in valence band. Low conductivity, semiconductor, small band gap. Conductivity depends on temperature, light, and doping. Doping adds impurities to control type of charge carrier. Superconductor, zero resistance at a low temperature due to special electron pairing. Bum, 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 bum. Bum, 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 bum. The band gap is the energy difference between top of the valence band and the bottom of the conduction band. What decides the side difference based on the atomic structure and binding of the material. Types of atoms, the energy levels of the valence electrons depends on the atomic orbitals and their energy differences. Example, carbon, very strong CC covalent bonds, large band gap. Insulator, silicon weaker, silicon bond, smaller band gaps, semiconductor. Atomic orbital overlaps, how much more overlap bands spread out, smaller gaps, less overlap bands narrow, larger gap. Crystal structure, the geometry of the lattice affects orbital overlap and symmetry, affects band gap. Example, diamond versus graphite, same atom but different crystal structure, very different band gaps. Bonding type, covalent bonds, electrons shared, band gap depends on the bond strength. Ionic solids, very strong bonding, usually large band gaps. Metals, conduction and valence band overlap, no gap. Crystal geometry of this lattice affects overlap and symmetry, affects band gap. Example, diamond versus graphite, same atom but different crystal structure, very different band gaps. But what changes in graphites, like individual atom wise, what's the difference? I don't really know. Like individual carbon atom wise, what are the difference from diamond and graphite, and how does those difference affect the energy gap? Energy gap. Covalent bonding, electron shared, band gap depends on the bond strength. Ionic solid, very strong bonding, usually large band gaps. Metals, conduction and valence bands overlap, no gap. External factors, temperature, increasing temperature can slightly reduce band gap. Strain slash pressure, compressing a lattice can change orbital overlap changes. E.g., doping can introduce. The doping thing. It's like adding another. So how is the lattice gonna be when you dope? Huh? Undoped, N-type doping, P-type doping. Okay. Dude, I have a lot of questions. That's weird. I need to get this topic over, man. The hell? Atomic structure: carbon is sp3 hybridized, forming four strong sigma covalent bonds with four neighboring carbons in a tetrahedral 3D lattice. Tetrahedral. That's diamond. Okay. Band gap. Reason: valence electrons are strongly bound in the sigma bonds, leaving a large energy difference between valence and conduction band. Empty anti-bonding orbitals. Okay. Here, bonding and empty anti-bonding orbitals. Why is the? I thought it was pi. Why is here the conduction band considered anti-bonding orbital? I thought it would be the pi sp3 pi 2p pi bonding orbital. And graphite atomic structure: each carbon is sp2 hybridized, forming three sigma bonds in a planar hexagonal lattice, and the fourth electron remains in an unhybridized p orbital, perpendicular to the plane. Perpendicular to the plane. Plane of what? That's the key point. It's a subtle distinction between molecular orbitals in molecules and energy bands in solids. Conduction band in a solid. In a solid like diamond, the valence band consists of filled bonding orbitals. The conduction band is the next higher set of orbitals that electrons can occupy, which is anti-bonding. 2p pi orbitals in diamond. The empty anti-bonding orbitals for... Why not pi orbitals? In diamond, all carbons are sp3 hybridized. There is no unhybridized p orbitals left. So no pi bonds exist. Mm-hmm. Mm-hmm. Okay. Now, from let's let's consider an organic matter like a piece of meat. The carbon in that would be sp or sp3, nothing more. So it would be a better conductor than diamond in that sense. Comparing molecular orbitals in C2 or CO. For small molecules, not quite. Here's why. Even if carbon in organic matter is conductivity doesn't actually improve just because of the hybridization. All diamonds, organic matter, meat, proteins, fats, mostly sp3. What? How? Some sp2 in double bonds. Okay. Plus, meat contains a lot of water and ions, which dominate actual conductivity in practice. Okay, actually, it makes sense. Carbon does have sp3. I kind of get it. Let's move on. Properties of gases and liquids. Okay, it looks like I'm done. Looks like I'm kind of done with the chemical bond, and I need to make a short video writing down everything I learned about chemical bond, but before that I will write a summary on what are the things I understood on the chemical bond with the difference and examples. So you have to let me know what are the mistakes I have made on my sample explanation, which I will be doing. Okay, looks like I could looks like I could go into wait sequence analysis, because that shit's still there. Okay, I think I could end the stream. Perfect. Go ahead, write your summary. If I write the summary, let's read on properties of gases and gas pressure. Gas consists of single particles atoms, nucleus moving fast, 500 meter per second for n2. At between the particle, there's ample space. No, so particle to particle interactions are low. The pressure of gas is the force that is applied by the gas. The unit pressure of Pascal pressure results in multiple collision of gas. P results in the multiple collision of gas particles with the wall of vessel confining the gas. P is measured by the manometer. Manometer. Possible units of P are Pascal, Newton per meter square, atmosphere, torr bar. The atmospheric pressure at sea level is equals to Boyle's law. The volume of a fixed quantity of a gas maintained at a constant temperature is inversely proportional to the pressure. Volume is inversely proportional to temperature. V equals constant times 1 by P. Boyle's law can be explained in the way that if a gas is compressed, a large number of atoms, molecules can be found in the smaller volume, so pressure of a gas rises as higher number of molecules, atoms per unit area collides with the walls of the vessel. Gay-Lussac's law. The volume of come on, gay is not a funny word now. Uh, Fixed quality of a gas is constant pressure directly proportional to the temperature. The pressure P of the fixed quality of gas is directly proportional to the temperature T. Gay-Lussac's law can be explained in a way. Okay, the volume is proportional to temperature. Gay-Lussac's law is explained in the way that if the temperature of a gas rises, also average velocity of the gas molecules particles increases, so collide more often with the higher speed in vessel walls. This leads to increased pressure. Alternatively, if the pressure is kept constant, the volume occupied by gas increases. Avogadro's law. The volume of the gas maintained at the constant pressure and constant temperature is directly proportional to the number of moles of gas. So maintained at the constant pressure and okay, so if pressure and temperature are constant, then volume is proportional to the number of moles of gas. That makes sense, right? Yeah. Ideal gas. Okay. Ideal gas equation. The previous gas law can be combined to an ideal gas equation. PV is equal to nRT. Oh, this is what made me pass a lot of exams. Thereby, the gas constants R equals. Okay. The ideal gas equation describes the independence of P with T, V, and N. The ideal gas equation is based on the following assumptions. The molecule atoms of an ideal gas do not interact with each other. The combined volumes of the molecules is much smaller than the volume the gas occupies. The combined volume of the molecules is much smaller than the volume the gas occupies. The combined volume of the molecule is okay. In ideal gas, there's no interaction between the atoms. The combined volume of the molecules is much smaller than the volume of the gas occupies. Okay. Hey, Dalton's law of partial pressure. The total pressure of a mixture of gases equals the sum of partial pressure. The pressure each gas would exert if it was present alone. The total pressure of a mixed gas equals the sum of partial pressure. Dalton's law of partial kinetic molecular theory of gases. Random motion. Kinetic molecular theory of gases. Theory of gases. Kinetic molecular theory of gases. It's still there. Diffusion. Diffusion is a random, undirected motion. Properties of liquids and solids. Molecular interaction in the liquid phase, whereas the formation of chemical bond is seen as strong interaction. The following weak interaction between molecules are discussed. Dispersion force, dipole-dipole attraction, hydrogen bonding, ion dipole interaction. Dispersion forces, induced dipole They are okay. Intermolecular horsepower, viscosity, phase diagram. I gotta look into his phase diagram. Redox reaction. Thank God I know a little bit on this. Okay, looks like I'm done. Looks like I'm gonna stop the general chemistry stream and continue with uh, sequence analysis. But before I continue on that, I should take a little bit, not a break. I need to steam. I need to steam my nose because this thing is fucking annoying, bro. Peace out, YouTube.